ordinary room. Or is it? And things get worse. What's going on? We get a clue by looking at this chair. It's not a chair at all. So, can you trust your eyes? Well, with the camera here, looking through a pinhole here, what you actually see is what lies along your line of sight. It doesn't matter where on that line the points of the chair are, we'll still see it as a chair. If we look from somewhere else, the illusion is spoiled. That's the trick behind this strange room. It's called a stenope room, from the Greek word meaning pinhole. This particular room is in the Cité des Sciences in Paris. Your line of sight is through the keyhole. You have to place your eye there to see inside. The floor and walls of the room are arranged so that one half of the room is much closer to your eye than the other half. And each half is a different size. Your eye has to infer the various sizes from the information that it collects strictly along the line of sight. Your brain processes the information it receives in the most rational way possible, based on past experience. But what happens in this situation is that the brain's interpretation is quite different from reality.
You may be asking yourself what this has to do with mathematics. Well, mathematicians and artists can actually make this visual effect work in their favour. Look at this woodcut by Dürer that dates from the 15th century. It shows an artist studying how to use a screen to help draw a realistic representation of the three-dimensional object on a two-dimensional canvas. Each point of the figure is joined along the line of sight and through the screen to the artist's eye. We say that the figure and its image on the screen are in perspective. In the same way, then, we can make a perspective copy of any figure in a plane in any other plane, just as this simplified model of projection does. Light from a projector here shines through a frame of film. Each frame of the film is part of a plane. The image after projection lies in another plane. In cinemas, the picture looks very like the original, but we could make it look very different by rotating one of the planes so that the two are no longer parallel. And later in this program, we'll use this idea of perspective in a quite unexpected way.
Now, interesting things can happen to figures in a plane if we cast their images onto another plane using projection from a single point. The new images can look very different from the old ones. The key feature of figures under projection is the lines of sight, the rays from some fixed point. A family of lines through this fixed point is capable of generating all these different pictures when it intersects with different planes. To formalise this idea of rays, we start with any point in R3, say the origin O, and take the family of lines through the origin as the points of a new set that we call the real projective plane, RP2. Every element of this set, every line through the origin in R3, is called a projective point. For example, given a plane π and a point O not in that plane, we can associate with each point P in the plane the line through both O and P. When this Euclidean point P sweeps out a line in the plane π, the line from O to P sweeps out another plane through O, and we call that plane a projective line. But what about Euclidean lines through O that are parallel to the plane π and so never meet π? We call these the ideal points with respect to the plane π because we can only have an idea of them in the plane π.
Let's look more carefully at how Euclidean and projective figures relate. We start with a Euclidean plane π not through the origin. For each point in this plane, we get the corresponding projective point by joining it to O. It's a Euclidean line through O. Given a Euclidean line L in this plane, we draw in the Euclidean lines through each point of L and O. This gives the Euclidean plane through L and O. And that's what we call a projective line. Or rather, what we have so far is the Euclidean plane through O and the Euclidean line L, with exactly one line in the plane missing. This one, which is a Euclidean line through O that is parallel to the plane π. And earlier on, we called this an ideal point for the plane π. Now, suppose that we start with a triangle in π. What does that correspond to in 3 dimensions? Well, each side of the triangle corresponds to a part of a projective line, and that's a Euclidean plane through O. So, we get 3 projective lines, which are all Euclidean planes, each pair meeting in a line, a projective point. The projective figure that corresponds to the Euclidean triangle in the original plane is this unwieldy cone-like object.
Fortunately, we can draw Euclidean figures corresponding to projective figures by seeing the intersection of the projective figures with Euclidean planes in their path. We start with our projective figure of various projective points and lines. Remember, these are Euclidean lines and planes through the origin. Here's where the projective figure intersects a plane π, not through the origin. It's called a plane of section. And if a Euclidean line through the origin meets this plane of section π, it meets it at a Euclidean point. If a Euclidean plane through the origin meets π, it meets it in a Euclidean line. You can think of cutting the projective figure with the plane π as taking a cross-section of a projective figure. Most projective points correspond to Euclidean points. Most projective lines to Euclidean lines. But some projective points do not correspond to any part of π at all. If the projective point is a Euclidean line through the origin that's parallel to π, then it doesn't meet π. And these projective points are the ideal points of π. Whatever plane you use for a cross-section plane, it has ideal points. Each time they lie in a Euclidean plane through the origin that's parallel to the plane of section. But that Euclidean plane must be a projective line. So, because all the projective points are ideal points, we call that projective line an ideal line. We can, of course, vary the plane section we choose. We get different Euclidean cross-sections of the original projective figure.
So, you've now seen that we can start with a Euclidean figure, pass to the projective figure it generates, and take a second, different Euclidean picture of that. We call this mapping from one plane to another a perspectivity. The figure on the right-hand plane is joined by lines to the origin on the left. That gives the projective figure. It is then cut by the plane in the middle, giving the second Euclidean figure. When we do this, parallel lines in the first plane may correspond to intersecting lines in the second plane. Now, it's worth seeing how that comes about because it's useful mathematically. We join the parallel lines AB and CD in the ground plane pi1 to the origin O, which we think of as an artist's eye. The planes OAB and OCD meet along a line L through O that is parallel to the plane pi1. That's the projective figure. These two planes through the origin cut the picture plane pi2 in Euclidean lines, of course. But because pi2 is not parallel to the line L, the new Euclidean picture shows two Euclidean lines that cross. Now, conversely, we can map any given intersecting lines to parallel lines under a projection onto another plane. Suppose the lines meet at some Euclidean point P. Then we choose a plane pi in R3 through the origin that's parallel to the line OP. The given lines each map to some Euclidean line in pi. But P doesn't project to any point in pi. So P must correspond to an ideal point for pi. And that means that the image lines in pi must be parallel lines.
So, you can map a pair of intersecting lines onto a pair of parallel lines by perspectivity. Can we simultaneously map two pairs of intersecting lines onto two pairs of parallel lines by perspectivity? The remarkable answer is yes. For example, we can map this quadrilateral onto a parallelogram. How? Well, choose some point O, not in the plane of the quadrilateral, as the centre of the perspectivity. Now, extend opposite sides of the quadrilateral, the lines that we want to make parallel, until they meet. Next, take another second plane, not through O. To make the first pair of lines into parallel lines, we must position the second plane parallel to this line. To map the second pair of lines onto parallel lines, we must also position the second plane parallel to this line. And with this choice of the image plane, this perspectivity maps the quadrilateral onto a parallelogram, just as we wanted.
Now, we've seen how to use Euclidean planes to get Euclidean figures from projective figures. So let's think for a moment about projective space itself, the space of all lines through the origin. Given any two distinct projective points, in other words, Euclidean lines through the origin, we can find a projective line through them. That's a Euclidean plane through the origin. So the projective line through any two projective points must be unique. Suppose, on the other hand, that we start with two projective lines. Each of these corresponds to a Euclidean plane through O. These planes must meet in a Euclidean line through the origin. So in terms of projective geometry, it follows that any two projective lines meet in a projective point. Now, remember that in Euclidean geometry, Euclidean lines don't necessarily meet. They can be parallel. So there's no analogue of parallel lines in projective geometry. As you will see, the fact that projective lines always meet often simplifies proofs in projective geometry. That's because in Euclidean geometry, we always have to separate out the two cases of whether a pair of lines meet or are parallel.
What sort of theorems could there be in projective geometry? Theorems about projective points and projective lines? Well, projective theorems must be about properties of figures that don't change under perspectivities. What are the properties? Well, first, collinearity. If three Euclidean points lie on a Euclidean line, the corresponding projective points are three Euclidean lines through the origin and those Euclidean points. The Euclidean lines lie in a single Euclidean plane through the origin. If we map this plane onto another plane by a perspectivity, the images of the 3 points on a Euclidean line in this plane must be 3 points on this line in the image plane. So the images of collinear points are collinear. And collinearity is the sort of property we are looking for. In the same way, the images under a perspectivity of any 3 lines meeting in a point will always appear either as 3 lines meeting in a point or as 3 parallel lines. So, concurrence of lines is another property of perspectivities. And so, the basic properties of projective geometry are collinearity and concurrence.
We're going to use our ideas about perspectivities to prove a famous theorem in projective geometry. It's a result discovered by the French mathematician and architect Gérard Desargues in the 1640s, when he became interested in drawing perspective copies of figures. This theorem concerns 2 triangles in perspective from a point O. The triangles are here labelled A, B, C and A', B', C'. Then, if the lines BC and B', C' meet at some point P, CA and C'A' meet at Q, and AB and A'B' meet at R, then the points P, Q and R lie on a line. To prove this, we use the technique of mapping the picture as shown earlier in the program. We can map this Euclidean picture by a perspectivity onto another plane in such a way that 2 of the points, say P and Q, don't appear. They become ideal points. That means that we map this figure by a perspectivity onto another plane in which the lines BC and B'C' are parallel, and the lines CA and C'A' are parallel. You saw how to do this earlier. That puts the points P and Q on the ideal line for this plane. Desargues' theorem will be true if we can show that R is also on the ideal line. So, we want to show that if BC and B'C' are parallel, and the lines CA and C'A' are parallel, then the lines AB and A'B' are also parallel. Once again, we measure distances from O throughout. OA equals A, OB equals B, and so on until OC' equals C'. Now, we look at the similar triangles OAC and OA'C'. Because the lines marked with a single arrow are parallel, we deduce that A over C is equal to A' over C'. Similarly, when we look at the similar triangles OBC and OB'C', because the lines marked with a double arrow are parallel, we deduce that B over C is equal to B' over C'. We divide one of these equations by the other and deduce that A over B is equal to A' over B'. Now look at the triangles OAB and OA'B'. Since the sides are in proportion, we now deduce that the lines AB and A'B' are parallel, which is what we wanted to show.
We've seen that a number of surprising results can be proved by using this trick of projecting a given Euclidean figure in one plane onto another plane by perspectivity. Now we can compose one perspectivity with another, indeed with a whole sequence of them. These compositions turn out to be precisely the most general kind of transformation of space that maps projective points to projective points and projective lines to projective lines. We call these compositions projective transformations. Just as every affine map is a sequence of parallel projections, every projective transformation is a sequence of perspectivities. The fascinating subject of projective transformations forms the subject matter of the next part of your work on projective geometry, which can explain a variety of visually stimulating illusions.
Now on